Hello there, this is my black hole lab for PHYS 2211. To introduce what we're doing here, our mission is to find solutions to two goals, which first of all we're going to find in part one, the mass of a black hole given the trajectory of a star. And secondly, in part two, we'll find the velocity needed to approach a black hole without crashing into the black hole or the planet that it's being launched off of. So we're trying to find the velocity to barely approach the black hole. What are models and physical principles? They include Newton's law of universal gravitation, as stated before in a previous lab, curving motion, changing momentum, and position and velocity update formulas. What will happen? As a brief overview, we will obtain a reliable calculation of the black hole's mass through many trials, in over 400 trials overall, and our spaceship will barely escape the black hole's wrath, luckily. Here is a model of the forces in both the p hat direction, which is parallel to the velocity, and also n hat, which is perpendicular to the momentum slash velocity. For our main physics ideas, Newton's law of gravitation states that F equals gm1m2 divided by r squared times r hat. We're also using the decomposition of F net into F net parallel and F net perpendicular. And since Newton's second law states that F net is dp dt, we can say that dp dt parallel equals F parallel, and dp dt perpendicular says equals F perpendicular. And here is our good friend velocity and position update formulas stated right here. And to find r hat, or gravitational force, you would just say that r equals r system minus r source, and then divide r by r magnitude, which is just norm r and glow script. Very convenient way to find that. Here's part one, mass of the black hole. Here's our model to calculate how the star would move around the black hole. Our constants are g, mass of the star, delta t, t, and also our x and y velocities in a list format that we're iterating through. And here's the meat and potatoes of our code here. We're finding basically the initial and final momentums, or p, using mass times the given initial and final velocities. And here's delta p and delta v, which are just doing final minus initial for velocity and momentum. dp dt is just delta p divided by delta t, and same thing for F net equals dp dt, because that's because of Newton's second law of motion, which is given by default, I guess. And p hat is the normal vector of p initial, and same thing with d magnitude. P divided by dt is equal to the change in magnitude divided by delta t, and dp dt parallel equals d mag p dt times the p hat vector to solidify the actual vector for the change in force or momentum in the parallel direction. And same thing with perpendicular. Similar process, just rearrange the variables a little bit, and here is the F net perpendicular equals dp dt perpendicular. And the radius is used to find basically the mass of the black hole using the gmm over r squared times r hat formula to find that it's equal to the magnitude of F net times radius squared divided by g times star mass. And our actual mass of black hole we found to be 1.48 times 10 to the 34th kilograms. And here are the rest of our forces as well. And here's the diagram that we use to illustrate the forces acting upon the star at every point in its orbit around the black hole. Part two, don't crash. Here's our model as well, which is very simple at first because we have the constants here and also the way to find the initial velocities and speeds. And our model was used to find the r from the black hole to the planet and from the ship to the planet to find its force using Newton's law of gravitation. And we found the net force on the planet and net force on the ship using the sum of both forces that were applied gravitationally by the planet and ship, by the ship and black hole, and here it's by the black hole and the planet. And the velocity update formulas were used to find the velocity and position at each point to make things move, to make the planet and the ship move based on where we were in simulation and to make things more realistic. So here's how we found the ship and planet's velocity and positions at each point. And our findings were that the velocity to escape the black hole while still approaching it closely was this vector. And it basically went vroom, approached the black hole without actually touching it, and then escaped it down this angled path over here without crashing into the planet or the black hole. What are possible errors here? They include the fact that the models don't account for outside forces besides the gravitational force, which is a little bit simplified. This is merely a hypothetical model, and we know that actual physics deviates heavily from theoretical physics. I did plug and chug for the initial velocity in part two instead of actual calculations, and the constants in the model, like the mass of the star in part one, are very simplified values that don't match up to realistic values in the real world. Those are possible error sources / inaccuracies. And what does this mean, and what if for hypotheticals? How are the net force and its parallel perpendicular components different from the rate of change of momentum and its components? Although they're the same thing mathematically, dp dt is much easier to calculate than F net because all you need to do is find the mass and also the initial final velocities, as opposed to finding every single force acting on the system in every single moment. That is way too much work for finding just the dp dt. What if we wanted to find the spaceship to enter the black hole's orbit? Well, in that case, I was able to find such a trajectory by using the following initial velocity of -4 times 10 to the 5th, 1 times 10 to the 7th, and 0 meters per second. And that caused it to not crash at all into the planet or the black hole as shown here. So cyan is the color of the, cyan is the color of the planet, and purple is the color of the spaceship, which is going in orbit around the black hole without crashing into anything. So it's very cool and very sweet. Thank you for watching, and I'll see you guys next time. Bye.